Hi everyone, this is a short presentation on dispersion in columns. Ideally, we want sharp and well-resolved peaks as shown on the left. However, dispersion could result in broad and poorly resolved peaks as shown on the right. In plain language, dispersion is the broadening of solute bands as they travel through a column. Let's now have a closer look at dispersion in chromatography columns. Dispersion can be measured using different metrics. One such metric is the plate height. According to the Van Deemter equation shown on this slide, the plate height can be obtained as the sum of three terms, these being the eddy dispersion term, the axial diffusion term, and the transfer term. In the Van Deemter equation, A is the eddy dispersion constant, B is the axial diffusion constant, C is the transfer constant, and U is the superficial velocity. The superficial velocity is obtained by dividing the flow rate by the area of cross-section of the column. The Van Deemter equation suggests that U has opposite effects on the axial diffusion term and the transfer term. This is evident when we plot H as a function of U. At lower velocities, the axial diffusion term dominates, while at higher velocities, the transfer term dominates. At the optimum velocity, that is at U-opt, these terms have their minimum impact and therefore the plate height is minimum. This corresponds to the best condition for separation using a column. Let us now discuss each of these dispersion terms. The eddy dispersion term quantifies dispersion due to variability in solute path lengths within the stationary phase. It depends on the size and size distribution of the stationary phase particles packed within a column. The greater the size, the greater the dispersion. The greater the size distribution, the greater the dispersion. Eddy dispersion also depends on the evenness of packing. The more uneven the packing, the greater is the dispersion. The axial diffusion term quantifies band broadening within the column due to diffusion in the axial direction. Diffusion takes place both at the leading and the trailing front of a solute band. The lower the superficial velocity, the greater the extent of axial diffusion. Axial diffusion has a significantly greater effect on the dispersion of small molecules and is less significant with macromolecules such as proteins. The transfer term measures dispersion due to the transfer of molecules from the mobile phase to the stationary phase. With porous stationary phase particles, the molecules are further transported within the pores. These molecules then have to be transported back to the mobile phase, and this back and forth transport happens over and over again as the solute band is transported along the length of the column. If the superficial velocity of the mobile phase is too high, not all the molecules present in a given location within the mobile phase get the chance to be transported to the stationary phase adjacent to it and simply get pushed down the column. Such partial bypass results in the spreading of the solute band. The transfer term is more significant for macromolecules than for small molecules. Let us now discuss how plate height in a column is experimentally measured. A pulse of a tracer solute such as acetone or sodium chloride is injected, and the tracer peak as obtained at the column outlet using an appropriate detector is then used to calculate the plate height. The tracer solute should not interact with the stationary phase, but should undergo all manner of dispersion discussed in the previous slides. With sharp tracer peaks, we use the equation shown on this slide for calculating plate height. N is the number of theoretical plates, Tr is the retention time, W is the peak width at the baseline, while L is the length of the column. In columns where dispersion is significant, the tracer peaks look like the one shown on this slide. With such peaks, objective measurement of peak width at the baseline is quite difficult. Therefore, we measure the width at half height and use the equations shown on this slide to calculate the plate height. The dispersion effects that we have discussed in the context of the Van Deemter equation are all microscale effects that happen in and around the stationary phase particles. Such an analysis of dispersion is sufficient for narrow columns, such as those used for analytical chromatography. Process columns that are used for preparative separation and purification tend to have relatively larger diameters. When using such devices, we also have to consider any additional dispersion, such as that due to the flow within the different parts of the column. In process columns, we could expect significant macro-scale convective dispersion at the column inlet and the outlet due to significant amount of radial flow within the column headers. Consequently, we could expect a solute band to get distorted as shown in the figure on the right. In effect, a molecule traveling along the axis of the column would travel a shorter distance than a molecule traveling along the wall of the column. Also, the average velocity of a molecule traveling along the axis would be greater. How do we factor in such column-related dispersion effects? One possible way is by modifying the Van Deemter equation by adding an additional macroscale convective dispersion term, as shown in this slide. However, if the macroscale convective dispersion term is dependent on parameters such as the superficial velocity, we would have to find out the exact nature of such dependence and factor for it. With very wide columns, we can sometimes see the so-called infinite diameter effect. When the column diameter is very large compared with the solute pulse volume, the solute pulse molecules exit the column without getting any chance to reach the wall of the column. This makes it difficult to interpret and use plate height data obtained, as discussed earlier, in any meaningful way. So when it comes to process columns, there are several additional factors that would need to be considered while measuring dispersion. Maybe we could use a totally different approach to the one discussed in this presentation. Step change experiments with tracer solutions would give more meaningful information on the dispersion in very wide columns. Also, computational fluid dynamics, or CFD, would perhaps shed some light on the goings-on. This brings us to a practical question. How do we minimize macro-scale convective dispersion in process columns? But that is perhaps a story for another day. For the moment, have fun with chromatography, and thanks a lot for watching.